Thank you very much. And well, I'm actually here covering for what was supposed to be Peter Hoppener's talk. So big shoes to fill. But I hope I will be able to go with you through the strategies in order to optimize the Terahertz emission from spintronic devices. So what will I be talking about? There will be a quick introduction on the model and the generic idea that will be quick. Everyone heard about this today. Then after that, I will discuss what are the strategies that we employ that are basically can be summarized in passive and active strategies on the emitters. And then the part that is a little bit more original of this presentation is how do we treat the spinol effect in regard of the energy dependence of the spinol effect. This is like the core of this work. Then we will show the results that we have and also give a little bit of a comment on some experimental insights that we have. So let's go. I guess we saw this figure at least 2 or 3 times this evening. So what do we have? We have an object which is made of a ferromagnetic and a non-magnetic part. We throw a laser on the object, we shine a laser on the object, and an electromagnetic wave gets emitted. Our question is, how can we build this object in the way that makes our signal the most wide possible, so big amplitude, and the most wide also in the frequency space, so big bandwidth. What do we do? First, let's have a look at how we do model this kind of system. We do use the superdiffusion model, which is, has been already discussed and explained by Marco. I mean, he made the model, so. But I will go quickly through that. The model gives you the dynamics of the electrons that spin, that are excited from an external laser source, and says, okay, the population of the spin is either affected by internal mechanics that can be the scattering of spins on other spin, and this is inside this phi operator, the scattering operator, or they can just naturally decay according to their population properties. And this is taken into account in this n over tau term. This is this is most of the ingredients of the superdiffusion model. While we take into account this, then we are able to get, as a result, a spin current that from the ferromagnetic layer goes into the non-metallic one. And once we are there, through inverse spinol effect, we are able to get a charge current. Now we have the current. How do we get the field? We use our beloved Maxwell equation. Everyone loves Maxwell equation. We use the retarded potential that are a solution for that. And by the definition of the field and the retarded potential, we get something that is really similar to Jeffimenko equation, plus also with some algebraic trick. Also a J term, a term that depends on the current, and that goes up 1 over the distance square. Now, why this is important or not, here we are going, in the results that I'm showing, we're going to be really close to the interface of the material. So I'm really close, and the J term is going to dominate over the derivative term. It's like J is bigger than the derivative of J by a factor of 10, but the distance is really, really small. Now let's go into the optimization part. We can go for the beginning in the passive part of the optimization. We work on the design of our material. It has already been suggested before. We can work on the thickness of both layers. May that be ferromagnetic part or non-magnetic part. But we can also play on something else. We can change the cap before and after our emitter. And someone could also change the cap in between the interface, the properties of the interface between the 2 layers. I'm not going to consider this second option, but only the properties of the boundary of the system. So with this in mind, let's go and see what do we have. These are, okay, the color scale is not great given the projector, but trust me. These are the estimated bandwidth of Terahertz signal for ferromagnet, ferro, iron, platinum, and nickel platinum bilayer, in which we do vary the thickness of the non-magnetic layer and ferromagnetic layer on X and Y. And what do we see? Now, if you were looking into my computer, you would see that here and here there's a sweet spot along 245 and 25 something nanometers, in which the bandwidth seems to be optimal, seems to be the largest. And these values, as far as I know, are pretty close to what has been measured to be a good sweet spot for the emission. For information, in this calculation, the pulse duration is 10 femtosecond, and the laser beam is of 1.5 eV. This is an important value because in our model, all the electrons can be excited from Fermi energy up to 1.5 electron volt. That means that the electrons are taken from iron from minus 1.5 up to 0. And these will be the energies that are excited and injected into platinum. Remember this. But before that, let's have a look also at the spin sink. What happens here? Here I'm varying the, where is the laser? Here. The non-magnetic reflection coefficient and the ferromagnetic reflection coefficient on the X and on the Y. And what do we see? As a rule of thumb, a person could say, okay, if my signal is short, my bandwidth will be larger. So what happens here? When reflection is 0 at the boundary, so everything gets transmitted, that means that my current that inside the material is the shortest possible. It just enters and exits immediately. In this situation, we do have the largest bandwidth. But if I then have a look at the total integrated power, this is the lowest power that's in the device. So I'm gaining into bandwidth, but I'm losing in energy. Basically, I'm wasting a lot of energy. On the contrary, we get the minimum, let's say, bandwidth for perfectly reflecting interfaces, boundaries, but the maximum energy in the system. So everything I inject stays there. So in this situation, I guess something like more optimal would be in order to play with lower, but not exactly 0 reflection coefficient, and finding the color scale is valuable. A point in which we still conserve a good amount of energy in order to not waste too much. We also want something that's be energy efficient. But I was also talking about active strategies. What's the difference between a passive and an active strategy? A passive strategy is the shape of the device, the geometry, the composition, while the active one is what I do while I'm measuring. And in short, in essence, I'm talking about the laser pulse. As I was mentioning, one would expect a shorter pulse would give you a larger bandwidth, and trivially, one sees that. I will show that. But one can also try to send not just one pulse, but two. What happens in this case? We do try, but this is still a little bit in progress, so take that with a grain of salt, to send two pulses from both sides of a three-layer, ferromagnetic, non-magnetic, ferromagnetic. These two pulses are shifted so that the resulting current will interfere, where is it? Interfere destructively into the non-magnetic layer. That results in signals which should be shorter in time and so larger in bandwidth. There's still a little bit of tuning on this kind of calculation, but what do we get? Okay, this is just the pulse duration that gave us different bandwidths. We get a comparison of the double pulse procedure and the regular procedure. Here is just the values of the double pulse when I use different laser pulses and different delays. So I will send both two lasers of 10 femtoseconds with a delay of 1, 2, 3, 4, and so on. And that goes for the integrated power. I use the same thing. But the interesting part is comparing that with the material, with the B layer, in which I send just one pulse. And overall, every configuration, every thickness that I can choose gives me at least the same degree of bandwidth of the B layer case. And sometimes when I move a little bit farther, I could get an increase in the bandwidth. As I was saying, take this with a grain of salt, because there is some post-processes of data that is making this a little bit less trivial. But I think that with a little bit more of patience and looking the right material, I could find a sweet spot here as well, in which two pulses would give you a better, longer bandwidth with respect to the bilayer. But this was all for the designing. I also mentioned in the introduction something regarding the energy dependence of the spinol effect in this material and how that affects this. Spinol conductivity in platinum is quite peaked at low energies, and it gets lower and lower as we move forward from the Fermi energy. Remember that I said that we excite electron from 0 to 1.5 eV. That means that the electron that will be excited in platinum will carry with themselves a different, let's say, importance into the conversion of the spin charge into charge current. You can also combine this information with the fact that platinum density of states is pretty much peaked in between 0 and 0.5 eV. So combining these two information make me think that, okay, I'm injecting a current into platinum, but maybe not all those electrons, as I get them out of my simulation, will going to contribute as I expect. So I may take, for example, the electrons that are in the highest energy level, 1.5 eV, and let them decay according to their lifetimes that I was mentioning before, into the second to highest level. But at the same time, the second to highest can decay in the third to highest, and so on. So I can renormalize the density of my electrons according to their lifetime in order to give them the time to decay into the lower levels. Once I have this, I can use these new densities to recompute the current that I was using before. And after doing that, I can recorrect, I can recompute my bandwidth. What do we see? This is just a ratio between the calculation of bandwidth before and after this kind of procedure. And there's some kind of systematicity in the shape of the material, in how the correction changes with the thickness. It's a matter of the program, of the model in this case. It's not something that I did explain physically yet. We do see that thinner samples, they do a higher correction. They need a higher correction due to this procedure of decaying of densities, while thicker ones, they are closer to their value. After this, I would say that, okay, we discussed efficiency, we discussed procedure for design, we discussed also the correction of the spinol effect. We can have a look at experiments. Here we have data gently provided by Suhi, and we compared the emission profile of a cobalt platinum bilayer of 2 nanometers cobalt and 4 of platinum. There it is. And in black is the experimental data. In red is our calculation, which is close enough. I mean, before doing the platinum correction of levels, this bandwidth was quite larger. So I would say that combining the energy dependence of spinol effect and the results of our simulation, we get a good estimate of something that is close to the experimental value. It's not exact yet. Can it get better? Probably. Do I know how to do it? Not yet. But still, this is the result that I have now. And I would say that after this, I can go to the conclusions. In this work, we did a systematic analysis on how to make better, how to optimize the Terahertz profile of spintronic emitters. And yeah, we analyzed how the properties of the layer, the thickness of the layers, and the boundary properties of the emitters affect the bandwidth. We are trying to understand if a double pulse protocol would be a feasible strategy to use in this case. And yes, the energy-dependent spinol effect helps correcting some overestimates that we noticed being present there. And with that, I would say that that's the end of the talk, and I didn't have time to write thank everybody, but thank everybody.